Okay, so we're looking at question 10 on the mix exercise on vectors. Part A, show that the point A lies on the line L. Okay, and we are given the coordinates of A. So if I look at the I component, okay, so if we just check in the I component or the X component, if you like, it's 7. So for the equation of the line, what gives us the I component is this plus this. Okay, so if I write my equation of the line as a column vector, we can always do this. I like to do this because it's nice and short, plus lambda 3 minus 1, 1. Now, if we just check in the I component, we know that the I component will be given by I plus 3 lambda, because that corresponds to the I component. Okay, and that has to equal to 7. And therefore, lambda, if we rearrange it and solve, has to equal to 2. Okay, just rearranging this linear equation. So now we have lambda. Now we have to show that when lambda is equal to 2, we get exactly those coordinates . Okay, so lambda is equal to, now we substitute lambda equals to 2 into our equation. We have R is equal to 1, 1, 1 plus 2 bracket 3 minus 1, 1. And that gives us the position vector of R is equal to 7 minus 1, 3. So you've shown that when lambda is equal to 2, and therefore the point A has to lie on the line because we've used the equation of the line with lambda, our parameter, as 2. Okay, and therefore we've shown that when lambda is equal to 2, it gives us the 0.7 minus 1, 3, and therefore A lies on the line. So for part B, it's an absolutely standard question. To find the length of AB, we have the coordinate of A, and we have the coordinate of B. So to find the length of AB, we use the distance formula. So basically, if you like, you can find the vector AB, and you're just looking for the modulus of the vector AB. Okay, and that is given by our distance formula. And I'll do this all in one go. It's the square root of, let's start, 10 minus 7, so that's 3 squared, plus minus 2 minus minus 1, that's minus 1 squared, plus minus 1 squared. Okay, because that's 2 minus 3, and that gives us root 11. So it's a very standard, just an extension of the distance formula in C1, but in 3D. That is all it is, exact Pythagoras in 3D. So find the size of the acute angle between the line L and the line segment AB. So if I did B minus A, then I get a direction vector along the line segment AB. Okay, so let's just do that. So AB, the vector AB is B minus A, okay, is equal to 3. Okay, so I'm doing that vector minus that vector. Okay, so it's going to be 3 minus 1 minus 1. Okay, so that will give us the direction vector of the line segment AB. And we use that part of our equation of the line. That is the direction vector of the line. And we just have to show, we have to find the size of the acute angle. Now the formula for that is very straightforward. Let me just remind you. So we use the formula, so it's just going to be very straightforward. It's A dot B over, so it's the modulus of A dot B over mod A mod B is equal to cos theta. And I'll put a red box around that. That's the formula we use, which we need to know. And in this case, this A is different from this A here. This A is, let's say, this vector. And this B is, say, is the direction vector of the line. So we just now compute that. So I'll do that now. So it's going to be, let's do the dot product first. And remember, we're just multiplying the corresponding components and add in. So it's 3 times 3 is 9, plus minus 1 times minus 1 is minus 1, minus 1, and that is equal to 9. And that is to divide it by mod A, mod B. So the modulus of the first one is going to be root 11 plus root 11. So times root 11. So it's going to be 11. So let's just do this. So cos theta is therefore equal to 9 over 11. And we just simply have to find the inverse cosine of 9 over 11. And to two significant figures, theta is equal to 35 degrees. Just finding the inverse cos of 9 over 11. We don't need to change anything. The formula says take the modulus, but we've got a positive number anyway, so we don't need to change anything. Now for this part, often we can simplify the situation big time by using what we already have. So if we look at what we already have, and in fact, this diagram should make it very, very straightforward. Supposing this was the line L1, L rather, and supposing this is the point A, I'm going to draw A there. And supposing the point B is not an L1, but floating somewhere there. Well, we know the angle between AB and the line L. Let me just write this in. This is the line L. Okay. We know this angle, which we've just worked out, 35 degrees. And we know this distance between A and B, which is root 11. This is from the previous one. So just writing down what you already know, and we are looking for the perpendicular distance from B to the line. So what we are looking for, if I do it, we are looking for this distance there. That's the distance we're looking for. We are looking for D, the perpendicular distance. Now, once I've done this construction, which initially looks like quite a difficult question, once you've got this picture drawn out, I can immediately see that this looks like a GCSE trigonometry problem, where I'm looking for the opposite side of my right angle triangle, and I have the hypotenuse. So we can say that sine of 35 is equal to D, the distance we are looking for, over the hypotenuse, which is root 11. And therefore, rearranging it and working it out, so sine 35 times root 11 is equal to D. Therefore, D is equal to 1.9 to two significant figures. Two significant figures. So the key to this question is not the mathematical calculation, but the construction of the diagram.